In this video, what we're going to do is we're going to talk about some characteristics that are not part of ideal logic circuits we've been talking about so far. Let's go ahead and start with something rather simple, and that is because of the way gates are designed, the NAND gate is kind of the natural output of putting transistors together. So NAND, for example, have to be inverted to get an AND. Therefore, it's always, given a given technology, always faster. NOR the same way as OR. NOR is going to be faster than OR. We usually build a NOR and then invert it to get an OR. So if you have a choice of using that, the inverted ones are faster. And the other benefit they have is that a NAND function is said to be complete, and which means you can make all other gates. You just imagine it a gate you want to build or any circuitry you want to build, and you can use NAND gates, may use many of them, to build it. As you remember, for example, we can use this, we actually have done that, you can use this to build a NOT gate. You can use this to build a OR gate using using the De Morgan's theorem, and also you can use this to make an AND gate. So you basically can make any gate you want. That same thing is true for NOR gate. So that's one thing kind of getting out of the way, that there's a concept called the complete set, and an AND gate is a complete set. NOR gate is a complete set as it stands, because you can build everything else out of them, and an OR are not. Okay, great. So that's out of the way. The next topic we want to cover is propagation delay. And propagation delay, so far when we've done the circuitry, so let's say we build a circuit that, let's do a real simple circuit. We've done a circuit that has input coming in, and the input goes through a NOT gate, goes through a AND gate. Let's say we've got another input to make it a little more interesting, and it goes through a AND gate, and then it gets inverted, and then goes through another AND gate. I could use other gate, but then I have to go look up the data sheet for them, so we'll just keep it really simple so we can get our topic covered. Okay, and then I'm going to have output of F here. Okay, so in the past, so far, we've been really worried about logic. Can I tell the expression of F with respect to all that? That's great. Now what we're more interested in is how long does it take for this input to make it to output. So that's where we are really getting interested, is what is this thing. More important, a lot of times we're not even, you can't tell me, but you know what exactly it's going to take. What we are really interested in is propagation, maximum time it takes to go through this. So if somebody asks you a question, sometimes they might put it in terms of a critical path. What's the critical path through the circuit? What's the maximum time for propagation delay? Because F is not valid until A and B have propagated through the whole circuit. They have to go through this knot. A is the longest path, so as long as we figure out how long it takes for A to make it through, then we can tell the user once the input has changed, if you wait this amount of time, then F would be valid. So how do we do that? Well, in order for us to figure out what this is, we need to go back to the data sheet. We know this chip is 74LS08. We know this is 74LS04. So what we're going to do, we're going to go to the data sheet, and this data sheet, for example, is for a 74LS08, and then we're going to walk through the data sheet. We're going to get to a place where we're talking about propagation delay, and here is where they talk about propagation delay, right here. And you notice we're going to also have two options. If it's lightly loaded, like its gate is connected to 1, 2, 2, 3, 4 other gates, then you can use the low end number with the 15 picofarad is the lighter loading. But if you're connecting it to 10 or so, then you probably should be looking at the higher loading, which is 50 picofarad. So we look over here and we see that the propagation from low to high or high to low, they're kind of nice. They're both 18 for the high loading. So then what we'll do, we'll go back here and remember on our diagram, we say, okay, the propagation through this piece of the circuit can be as much as 18 nanosecond, and the same thing here. So I've got 18 nanosecond through there, 18 nanosecond through here. So I'm almost done for B here, because B's only have to propagate. Oh, I'll take that back. B has to go up here and propagate through here as well. But this path is going to be the shortest path out. But F is not done until A and B make it through all the other path and get out there. So let's go ahead and go back and figure out if we can find out what the 74 LSO4 delay is. So we're going to go back to online and we're going to look at the data sheet, which is the for 74LS. As you can see, this is the 74LS data sheet, and we've had to go quite a ways down the list before we found it. So the first page was basically how the package is set up, second page ordering information, how it's connected, how the internal is done, and then eventually we get to a place right here where we see the timing, we see the propagation delay. Since we went with the high loading on this one doesn't have high loading, so and if you're going to load it higher, we have to for ourselves degrade this. In this case, we actually have two different times depending on whether the output is transitioning from low to high or high to low, and we're going to go with the worst case scenario because we want to make sure we have the longest worst case scenario for getting the input to the output, and for this one it's going to be 22 nanosecond. Okay, so let's go back and put that one on. So this one takes 22 nanosecond and then 22 nanosecond. Okay, and so we're going to go back and just look at it again. Yeah, that's a 74. That's why it took so long. We actually this was a lot slower than I thought, so we need to go find a 74 LS04, not 74 that. So let's see if we can find that data sheet. So we just gotta thumb through this until we find it, and hopefully it's down here, and there it is. Oh, that's much better. That's much better. So you got to be very careful with these data sheets because they use the same data sheet for many different parts of similar characteristics, but then you got to really pay attention to what you're looking at. We were looking at the wrong one, so we would have been wrong. So now we're right. We're looking at the propagation that both of them are 15. So we're going to go back here and change this to 15 so it's correct. Now, if they're asking out what's the maximum delay through the circuit, how long after I change my input should I wait before the output is valid, you say, okay, the worst path through this circuit is going from here through this, through this, through this. All other paths are shorter than this. So if I want to do this, the maximum is going to be the maximum delay through this is going to be 15 plus 18 plus 15 plus 18. So it's going to be 15 plus 18 plus 15 plus 18 nanoseconds. So that's how long I have to wait. It's 36 plus 30. So I have to wait 66 nanoseconds before I'm sure that my input has made it through and my F is valid. So this is called the propagation delay and propagation delay analysis, and that's something we have to do if timing becomes a critical issue that we are worried about. Okay. One other thing that we haven't worried about up to now, but we should really start thinking about it, has to do with the fan out, fan in. That's pretty simple. It basically says that if I have a gate, let's say I have a NOT gate, okay, output of this can be connected to many other devices, other ANDs, other multiple ANDs, maybe a NAND, maybe a NOT, maybe a OR, whatever. So the number of outputs these can drive is referred to as fan out. We like to keep this well under 20. 20 is being kind of generous for LS. So that means you cannot connect the output of one gate to more than 20 of these things. If you do, the output would not have enough power to make things go. By the way, as you add more gate to your output, your propagation delay will get longer and longer and longer. Okay, so that's a fan out. What's fan in? Fan in, you also have to worry that some of these devices have a limitation of how many other inputs can they be connected to. The number of input they can be connected to is referred to as a fan in, and that is referred to we definitely, the fan in we want to keep under 20 as well, which is kind of a nice match. So fan out is how many gates can an output driver drive. Input fan in is how many inputs can be connected to each other. So you got to think about both of those and make sure the current requirements are satisfied from the data sheet. Okay, so now we talked about fan in and fan out. Finally, the last piece of this conversation is minimization across multiple functions. We've studied K-map and we've been told, and sounds like a good thing, the way to minimize the literal count, which tells us the complexity of our circuit, is do a Karnaugh map, find a minimum function you can write, and go with that. Once in a while, when you got multiple output, you also need to look across function to see if there is a better way to get a total, to reduce the total number of literal counts you have. I have a simple function here. Let's say we have a function which is function represent. We want to minimize function represented by the truth table, the following truth table. Okay, so that's what they're asking us to do. So let's take a look at this truth table. We got A, B, and C, our trusty inputs, and hopefully I will get all the eight of them. Oops, missing one. Got it. So we got 0, 1, 2, 3, 4, 5, 6, 7. Okay, and let's say this in our system, we actually should do my system diagram. We've got a system, A, B, and C coming, and they expect us to generate F1 and F2. Minimize functions. Actually, I should have said function represented by the following truth table. We got 3 inputs coming in, we got 2 output going out, then we have F2 and we have F1 represented here. So let's say for this one, we got 1, 1, 1, 1, 0, 1, 0, 1. And then for the F1, we've got 1, 0, 1, 0, 0, 0, 0, 0. Okay, so we've done this in earlier videos and you're getting familiar with this. So what you're going to do, you're going to do a Karnaugh map for F1 and you're going to do a Karnaugh map for F2, and let's do them both here. So I have F1 and F2, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, A, B, and C, A, B, and C, A, B, and C, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Great. So let's say this is F2 and this is F1. Now, using our traditional scheme, which works perfectly well, our F2 is going to be 1, 1, 1, 1. Then at 4 it becomes a 0, and at oops, that's 4. Yeah, 5 is 1, and that would be a 7. 7 is 1, and this would be 0. 1, 1, 0 would be 0. Great. And then when you come over here, and this one says basically that as we look at this thing, it says that 0 and 1, I'm sorry, 0 and 2, 0 and 2 are 1, everything else is 0. Okay. Then we'll come over here and we follow the normal process we've learned how to do. And we say, okay, the biggest prime implicants are this one and this one, great. And therefore my function would be, in this case, A0. Oops. All right, let's fix this before we go too far. A's here, B and C are here. A's here, B and C and here. I had the variables bundled. Okay, so now I've got A naught in here. So I've got A naught there, and then also the other big one is going to be here, which is going to be C. Okay, oops, or C. And then I'll go over here and take a look at this one and say, okay, what is the best thing I can do here? Best thing I can do here, I can grab this and this, and then that's great, because then I'll have A naught or C naught. Okay, so that's perfect. So now I have, for this solution, I have a literal count that is equal to 4 when I implement both of them, 1, 2, 3, 4. Now, the idea we want to illustrate here is that there is, if you look across both of them, you will see that it's okay to grab this one, but if you could grab a smaller version here and here, then you would have, then your F2 would be written as basically A naught, C and C naught, or C. Now you say, wait a minute, this is bigger than that. Why would I want to do bigger? The reason for that is A naught C is implemented here and is used here also. So instead of, so it's shared, if we call that a shared term. So if I write my F1 as I did before, then I can say my literal count is 3, because this is no complication. This is exactly the same as this. Once I build it, I'm done. So there's no additional gate required to build that. So even though I sub-optimize, even though this was not as minimized as this one, my total literal count went down. So you always want to be watching for that when you're doing multiple functions and somebody says to minimize it. You want to look across those functions and see, is there any places I can share terms to get a better total, or reduce the total number of literal counts, therefore my complexities. Before we stop, let's go ahead and go back and see, we've kind of talked about a whole bunch of stuff here. One was talking about the fact that the NAND and NORs are complete sets, and they're always faster in a given technology than their positive counterpart AND and OR. The other thing we talked about was propagation delay, the ability to go through the data sheet, look to see how long it takes for something to propagate through, so we could have a sense of what is the maximum amount of time it takes for our output to stabilize when we have changed the input, so we can take action based on the output. Fan in and fan out. The fan out basically says how many gates can I drive off of a single output. Fan in says how many other inputs can I connect a given input to. So those are, and both of them we want to keep under 20, well under 20, because as you get closer to 20, your speed really goes down, and you got to be watching that. And after 20, you have no guarantee it will work, because there might not be enough current to drive it. And last but definitely not least is this idea of being able to minimize across multiple functions, and be aware that if you suboptimize, minimize each function, you might not have the total minimum number of literals, counts, or complexity when you're finished. That brings us to the end of this video.